Welcome back to the stream. Trying to actually get started on time. So mostly the streams here have been pretty spontaneous, but trying to start at least having 2 scheduled streams a week on Tuesdays and Thursdays around about now, whenever this is in your time zone. This is 11 a.m. In US Pacific time, which is where I am. I think we're, let's see, I should just check what time it is in GMT right now, because I'm going to mess it up if I try to guess it off the top of my head. It is 7 p.m. GMT right now. Where's that UK time? What did I just find? See, I'm actually terrible at time zones. Okay, it's 6 p.m. GMT. 8 p.m. Central European time right now. Okay, so yeah, either this time slot or maybe an hour or 2 earlier. Okay, yeah, Tina's confirming that is UK time. Cool. Anyway, this one is going to be a shorter stream than the one yesterday. Yesterday, I asked the internet, put up a little Twitter poll to see what we should be doing, and let's see, I've got that right here. So hi, welcome. Oh, cool. 20 o'clock UHR in Deutschland. Yeah, so yeah, I realize this is a little bit late for most of Europe, but yeah, maybe it's all right. Let me know what you think about the time slot. I know, especially if I'm going to be doing super long streams, then like this isn't really like a workday stream. It's like a winding down for the evening kind of stream or something. But yeah, I'll try to see if I can get stuff together to start a little earlier. Maybe I'll even have to, like, you know, plan ahead slightly more than I already tried to. This stream is going to be simple, though. Yesterday's was this, let's see, it's right here. The mystery retro teardown was the surprising winner here. And that actually turned out to be a combination of this old Radio Shack audio amplifier, which was nothing special. It was actually even worse than I was expecting. I was expecting something with maybe a couple of TO220 power transistors in there or something, but instead there were some weird 8-pin dip amplifier, like monolithic amplifier packages. It was this weird package with an 8-pin plastic dip with a fin on one side, so very strange. Oh, time.is, thank you. I thought I had seen that before, and I always forget about it when I'm under pressure. I'm so bad at time zones and just all the arbitrary human stuff. Like unless I have like a good ground anchor I can use to figure out how something works from the basis. So really, I guess I just need to be better at like memorizing. I don't know. There's no good basis for time zones though. I mean, you can memorize kind of roughly like where the I guess maybe I need a globe with the time zones on it, and that would help, like a physical object. Maybe I can 3D print something like that. Or I've got a small globe. I could just, you know, use Sharpie or something. That would be useful. Yeah, so anyway, we did that, and that was actually pretty, okay, I didn't tell you what the main course was. The appetizer there was this kind of unspecial Radio Shack amplifier, which wasn't that great, but it's an interesting enclosure. Actually, someone on Twitter suggested we turn that into a MIDI theremin. Was that in this thread? That was elsewhere. That might be interesting. Because yeah, it actually has a sticker on it that says simulated walnut grain. So, oh yeah, the daylight savings time and all that will mess up my globe unless I have multiple overlays I can put on it. I mean, I guess I'll take like a WebGL globe or something. I'll permit WebGL for that. Actually, we should be able to do that with CSS, right? Have a 3D globe made entirely out of CSS that changes according to the time zone. That's a challenge for all you web developers. All All right, so anyway, after that, we actually spent quite a while digging into this voting machine teardown. Finally did get it to spit out stuff like this. Is this ever? Oh, actually, I don't have autofocus or auto exposure turned on. I have to turn on the camera here. So we did actually finally get the touchscreen to show some signs of life. But yeah, it's interesting. The touchscreen was erratic. Imagine that, an electronic voting machine with an erratic touchscreen. But yeah, sometimes it was just not responding at all. But one time when I booted it up, it responded normally, and I ran it through a calibration. I have a receipt from the touchscreen calibration showing that the calibration didn't even change much. So it's acting either like a software issue, or maybe more likely there's an intermittent connection in the cabling for the touchscreen. Do I plan to torture the paper to figure out its... Oh, no, I'm pretty sure this is just pretty garden variety, like receipt paper. There's nothing really special about this. I mean, it was a standard thermal printer in there. So yeah, I did manage to calibrate this. The clock is still set, so that was yesterday. Printer test. And we were like poking through the file system a bit. So it doesn't run DOS, it runs this other operating system, some kind of weird RTOS, the name of which is escaping me right now. And there's a lot of prior research on this. Like, there's already a website which explains how to run Doom on this thing, basically. I just wanted to kind of start from first principles here for fun and see what we could do just with the box in front of us. And so I didn't see a really rapid way in, but then again, I didn't really look at the main application that much. It looked like all the code was in this file, which seemed like it was just dumped into RAM and then run. And then there was a bootloader, which also seemed like it was just run. I was like struggling at first to see whether the bootloader was in 16-bit or 32-bit assembly. It seems like it's in 32-bit, but before the system is really set up, you know, other than, like, I think it's basically a BIOS that's been modified to just jump to a 32-bit code segment and then load a bootloader with a strange name or something like that. That's still an open question, is like how exactly, but the BIOS on here has been modified so that it boots in a slightly non-standard way, and that's why we couldn't just throw DOS on here. So I spent a lot of time yesterday just disassembling the bootloader to see how that actually worked. So this is like basically the last thing it was used for. It was apparently like the 2008 election here somewhere. I think this might be somewhere in California, but I don't actually know where this was from. But yeah, I mean, it has totals and stuff. There also were a bunch of write-in votes that got stored in memory. You know, and of course it doesn't have like identifying information for the people who use the machine, just the candidates, but all the text in here seemed to be stored in files in some kind of 2-byte encoding. See, a lot of people like the Doom on the ATM mod. I don't understand why that's so popular. This is a terrible gaming platform. Like, it's kind of... Like, I understand that there is a traditional kind of nerd cred that comes from that, but that's the only good thing that I see about that mod. Like, if you want to run a game on this, it seemed like it'd be better to run, like, Papers, Please, or, like, make a game about gerrymandering or something like that. But it's not a good game platform, so I'd love a project for this, but I don't think running a game on it is really the right project. I think that's... I don't really see the appeal in that. So yeah, there's a lot of places we could go with that. There's some more low-level reverse engineering we could do just to like go from first principles to running useful amounts of code on the thing. On the last stream, I did just make a proof of concept modification to the bootloader where I changed some configuration flags and strings. I didn't actually change the executable code, but I changed some stuff that the executable code was relying on and was in like the same segment. So It seemed like a pretty good proof of concept that nothing in the BIOS actually had a functioning chain of trust that it could use to verify the bootloader, so I could just change anything I wanted in the bootloader, basically. And so the proof of concept was actually to re-enable a feature which apparently had been really haphazardly disabled by the people who modified the BIOS, which originally let you, interrupt the boot process and get to a very simple, the bootloader shell only has a couple of commands. It really only lets you change what file you're booting off of. And it isn't totally clear what file systems it supports, but I did see code for FAT and IDE PIO mode hard disks. So, Madbugger's asking if the batteries work. It has some. It runs on lead acid batteries, and the batteries in there were flat. So it was like a 12-volt pack with 2 batteries in parallel, and it measured a half a volt. Maybe that could be revived. You could also get replacement batteries for not a lot of money. It's also heavy, and I'm actually kind of enjoying having the batteries removed from it right now because it makes the whole thing a lot lighter. You could put a different battery technology in there, maybe. Oh, that's a great idea. Marvel says that Germans traditionally install chess on voting machines. That would be a good game for this, because the touchscreen isn't really good for twitchy, fast anything. And it doesn't have buttons. You can add a keyboard trivially, but having a keyboard sticking out of the front of a Doom voting machine just feels kind of superfluous, right? I mean, the other thing is if the processing power is a limitation and this isn't considered cheating, the project could become how do you connect a Raspberry Pi to the voting machine's display so that it looks factory but has actually got a lot more processing power. It's got a somewhat lousy viewing angle, 1024 by 768 LCD, with a pretty old school resistive touchscreen, which, aside from the intermittent connection problem, which is presumably a cabling issue, it seems to be fine. So one way to do this, honestly, would be to put the Raspberry Pi entirely within the touchscreen portion of the unit, and then the rest of it just becomes like storage space for other stuff. Yeah. A portable logic analyzer. I mean, I think at this point, the portability aspect of it is nice, but only for things which would be made more portable by adding a suitcase. And I think there are probably logic analyzers like the Salier that are already, I can just throw them in my messenger bag. I don't need a suitcase. But if there's something that would be made more portable by adding a suitcase, maybe I can make some kind of awesome portable soldering station, or the thing that I'm most excited about is a portable audio-visual interactive performance thing that I could make. And I don't know if this is something I would use or something I would build for someone else to use, but something that you would use as, you get up on stage and then you have basically a micro photography and synchronized light and vibration environment that you can use to create real-time visual stuff for DJing, basically. So I don't know, maybe that's silly. Maybe some of you think that running Doom on a voting machine is a much better use of it than turning it into a platform for nightclub visuals or something. And maybe you're right, but I think they're both kind of just strange, superfluous uses, and perhaps the actual project is still hiding in there somewhere. Yeah, so anyway, that was yesterday. Just a quick recap. You can see the robots finding Tuco already a little bit. Oh, cool. A link to chess on the voting computer. Maybe we'll check that out really quick. See that? You just gave me a link, and I just opened it on stream like a chump. Yeah, right. So I said this a bunch yesterday, but just to be clear again, as far as I can tell, there is no known technological way for voting by computer just to be secure, because what we mean by technology here is a pile of abstraction, which is fundamentally obscuring what's going on. So even if you had some even if the protocol you used was perfect, let's say you had some infallible crypto voting protocol, whatever, you can't trust the end user terminals that much. If you imagine if some crypto voting protocol thing was now the standard, now everybody's personal computer or phone would become a huge target for basically national scale voting fraud. And everybody who votes on a PC that has a 0-day available, you might as well just install a rootkit on that person's PC that has them actually cast a different vote than they intended to cast. And you can't really protect against that without extremely good hardware level security, which just isn't practical right now. So yeah, as silly as it might seem, actually having a process which is fundamentally extremely simple and auditable by humans at every step is, I think the only way we have actually to avoid large-scale fraud. You can still have small-scale fraud, but the thing is, with a voting machine, we would have the equivalent of giving a vote auditor a trick pencil that actually writes different marks than they think it's writing or something. And we can do that with technology relatively easily, whereas that's just not really practical in the world of pencil and paper. So yeah, this specific voting machine that I found on eBay a while ago, so it's the Sequoia AVC Edge. It specifically has been shown to be insecure a bunch. There's really no new work to be done in debunking the security of these, only in sending a public message if that's useful, or in just creatively repurposing something which otherwise would have no useful purpose. Tuco's over here on this desk. Sometimes I forget where the actual camera is. This is why we need more software to actually manage the positioning of this thing for me. We're getting there. EM noise from the display. Yeah, well, if you're worried about that, this thing certainly did seem to have a lot of wiring in there to act as antenna service. Look at how old school this stuff is, wow. Oh, that's great. Yeah, that's fun. Okay, so it's a 68,000 power fraud. Yeah. Yep. Yeah, and these inspection seals are just as a reverse engineer, I can get a box like this on my desk and just there's no practical way to know the full extent of what's going on inside it. You can pick away at it, you can do experiments on it, but there's just no way to understand every single piece of it without exhaustive effort. And grinding away all the surfaces to make sure there's nothing hidden inside of any structural members and that kind of stuff, because you can get extremely obscure with modifications if you want to. But you don't even need to go that far, just even inspecting all the software to be sure that no backdoors have been hidden, which is obviously a lot more practical than hiding things in metalwork like they used to. Even that is just so much work that no one can practically do it for something like this, unless you have a lot of advanced warning and way more transparency. And yeah, and even if you have all the transparency from the people making the voting software, for example, you wouldn't necessarily have transparency from all the suppliers that they're relying on. And then you wouldn't necessarily have thought about all of the unintended consequences of, just imagine if there, I don't know, just so many components could be, could be overlooked if you're, if you're worrying about classes of vulnerabilities like Tempest especially, looking at the electromagnetic field radiated by your machine, and can someone nearby determine what the votes were? That's, I don't know, that's extremely hard to counteract. And I guess it depends on what your threat model is, but I'm most worried about rootkit kind of things where you can modify how it fundamentally works so that it is no longer transparent about Like it can, it can lie to you and hide the fact that it's lying if you have the ability to just put arbitrary code on there. Anyway, that's enough of an aside there. On this stream, I was actually going to make this probably a quick stream, but this was a viewer request. So we were going to take down the second choice here. We did the mystery retro teardown yesterday. Today I'm going to pick up this Wacom pen teardown. And so that actually came as a follow-up comment for this video from yesterday. So Sunny asks if we can tear down an old Wacom bamboo pen, the same one in this video. And so in this video, I went over how the tablets worked, and this pen that you see taken apart is a different brand. That's a Huion pen, which is a little bit simpler inside. And then to illustrate what was going on in the Wacom protocol, I took apart this this mouse thing, which is actually pretty cool in that it's just like large enough that the parts in there are, they're easier to disassemble, but they're also, it's all based around like discrete logic chips. So it was an interesting thing to take apart and get back to schematic. Where's Tuco? Oh, he's way over there. Oh, I think he just wants to hang out in the hallway now. So we went inside there and talked about some of the protocol, and here's actually the inside of that same tablet. This is our old friend, the Wacom Bamboo Fun, aka the CTE 450. I like these because they're inexpensive, or at least when I was looking for them, you could find them for like $10 on eBay. And so I've got a bunch of these with different firmware versions, and some of these are empty because I took the boards out to solder things on. Yeah, so I've done various experiments on these. They are kind of an interesting little hacking subject because it's just like a strange but pretty inexpensive and common piece of hardware, but you also have access to effectively a matrix of antennas here and an analog front end that can transmit and receive resonant pulses on those antennas. So here you're seeing an array of like loops that run vertically. So these are all overlapping coils that are maybe about that size. And then there's another overlapping set of coils and so on. So you can isolate, if you're receiving a signal, you can isolate kind of where horizontally it is by looking at the signal strength on those coils. And then the same way on the back, there's a, this is just a 2-layer circuit board. On the back, there's horizontal coils, which similarly overlap, but let you localize where something's coming from along the vertical axis. So the two different tablet technologies here were pretty different in that the Huion tablets up here, the pen is just a transmitter. So I don't think I have audio here. I don't think I want audio, actually. Yeah, so the pen here is just transmitting this signal here. I think this is around 700 kilohertz. And the frequency it transmits at depends on, oh wait, this is the Wacom Intuos, actually. Yeah, the thing the Wacom Intuos is like 750 megahertz carrier. Okay, this is the Huion tablet where I'm actually just simulating the pen using a signal generator. And so it's just receiving on the tablet end. The pen is just, the pen takes batteries and it runs this continuous sine wave oscillator, and the frequency changes depending on what's going on. It changes, the oscillator is actually detuned a little bit as the nib moves in, which is how it senses pressure, and it switches in different capacitors when you press the buttons to change the frequency in larger steps. So that's very simple. We took a look at that. We also took a look at the Wacom Bamboo Fun mouse, so this thing right here. And this one, I forget what the carrier frequency is for this one. Yeah, so this tablet comes in a kit. This is the actual unit we have here. And the mouse acts pretty much like the tablet, except they respond with different packets. So in both cases, there's a fundamentally passive circuit in here, which is energized by the field in the tablet. So there's no batteries in here. This is just powered up kind of like an RFID card would be by a carrier wave on the tablet. And then in the case of the mouse, it sends back a very simple packet, which just has the state of the buttons and the scroll wheel. There's a little logic circuit on here that actually latches the scroll wheel encoder a little bit. But it's pretty simple, and they do this all with just like 74 series logic. So the pen I expect to be a bit more complicated. So with the tablet here, or sorry, with the mouse here, yeah, we looked at the actual chips on there and took it down to a schematic. And I put this on GitHub, I think. Yeah. So there's a link to a GitHub repo where you can get the schematic from the mouse, if you want to take a look at that. Did this in KiCad. So yeah, I broke this down into a near-field I/O section and like a signal conditioning section. So this has outputs of scrolling down, scrolling up, whereas the inputs are the actual quadrature signals in. So this isn't optical, actually. Optical would actually require more power than we have because the LEDs are actually kind of power hungry in an optical sensor. So this uses a rotary switch encoder. So it's actually making contacts when you scroll this, but it's still in a quadrature pattern. So these low power logic circuits convert that quadrature into pulses for up and down, which then go out in the packet, which is built by a little shift register circuit here. So this is very simple. I kind of expect that the pen is going to have an application-specific IC in it. I'm not really sure how else they're going to do all the stuff they need to do in the pen. Because the pen sends out a digital pressure. So they're going to have, I expect, a strain gauge and an A to D converter, and then also some of the same circuitry for recovering power from the magnetic field here. Just generating impulses here. Yeah, this is like more relevant. Oh, I still have this circuit. What was this tuned to? It's just a tunable LC tank. Yeah, I think the Wacom stuff is around 750 kilohertz. So we can recreate this experiment, actually. I wanted to actually try out these pens before we take them apart, just to make sure that if it's... Well, it doesn't need to be working for us to take it apart, but I'd like to at least know whether it's working or not before we take it apart. All right. Let's see if I've got the right cable for this. Need a mini USB. I'll be right back. So today's stream is we're taking apart the Wacom pen. So this is a viewer request to tear down and take a look at how the pen in this Wacom tablet works. This one. And so it seemed nice. Like that was something that I skipped when I made the first video, both to save time, because I expect it's not as easy to examine as the one that I did take apart, and because I actually only had one pen when I made this video. I have a few extras at this point, so I'm happy to take one apart. I expect that it's a destructive teardown, but that's why I got a couple. I just did not have that luxury when we did this last time. The sticker has a firmware version. It doesn't have anything else. Okay, CTE 450. Our old friend. So if I put this on top, it starts being a mouse. It still uses absolute coordinates, I think. No, that was weird. So it's relative. Well, I can't tell what the logic is for when it picks this up as a move and when it doesn't. Like sometimes it seems to warp and sometimes it doesn't. That's weird. But if I scoot it up against the edge like that, I can actually change the mapping, so it is relative. Which is what I would expect for no tablet drivers loaded. These tablets have like a default mode and like an advanced mode, which is what they use when their drivers are loaded. They're both hid, but the default mode I think is relative, so it acts more like a regular mouse. So that works. Let's try these pens. This pen, I don't know about that pen. This pen works. Do I have 2 broken pens and 1 working pen? Is it possible these are for a slightly different model? These are supposed to be for CTE 450. Maybe I've got 2 broken pens. Let me try a different tablet just in case this tablet is like picky about resonant frequency or something. The working pen still works. It's interesting that I don't even get motion, which would indicate the coil is probably bad. Because even without any active circuitry, these should do position sensing. Yeah. Well, let me use the working one to show you on the oscilloscope what I mean about this digital packet. Let's get that set up. So there are various ways we could pick up this signal. A big coil of wire would give us a nice high amplitude signal, but I think just a single loop of wire, if that's enough amplitude to read, will give us less additional resonance and we'll get a clearer view of what's actually going on. Okay, station 240 says that the Wacom pen disassembly is not necessarily destructive. That's cool. Okay, I'm gonna see how far we get by just adding a single loop of wire here. Carefully attaching that on. I might need a couple of smaller loops or something. We're like right down there in the noise. There's something visible, but let's try a little bit of a coil. I'll just grab a small inductor. Actually, I wonder if this works. This is not quite what I was looking for, but this is actually a UHF antenna. But I'm curious if just this is enough turns for me to actually pick up a signal. This is really just picking up noise mostly. I think we might actually need some resonance. I mean, I think before I actually had pretty good luck with a larger inductor, just like across the scope. Like, I think I've got some 10 millihenry inductors or something. Oh, is this what I was using before? I have an inductor with a resistor across it, which I might have added for damping. I bet this is what I was using for this purpose before. No, I could do FFT, but it just shouldn't be necessary. The signal should be much clearer than that. This is not a subtle signal I'm trying to pick up. Yeah. Like this is like an RFID reader. It's enough to power the circuitry in the pen. So this is not a resonant circuit. So in the actual pen, it would be using a resonant circuit to try to store as much of that energy as possible. And that's not what I'm doing here. I'm intentionally damping it a lot so that I can see more of the actual wave shape it's transmitting. So it's a series of pulses. It looks like we're switching to a different antenna, transmitting a pulse, switching to a different antenna, transmitting a pulse. And then here, we're actually reading those as different intensities because they're just physically at different locations. So right now, the tablet it doesn't know where the pen is. The pen isn't here, so it's just scanning around trying to find it. So you can see it switches modes. And now it's actually tracking the pen. And it'll actually start transmitting on the same antenna I'm right over when I'm on this same column. So I guess that tells us that transmits happen on the horizontal antennas and receive happens on the vertical antennas, because I'm not really getting much over here. And I can find the center of that antenna just by moving that around. So let me try to get this positioned and then try to get that wave to hold still on the scope. We don't need a stack of tablets for this demo either, as fun as that is. don't know if any of these triggers are gonna do me any good here, but maybe. Yeah, so that is the resonant frequency. Is that actually the resonant frequency of the pen? No, because here we're locking onto the carrier it's transmitting. I think that's actually just the oscillator in the tablet transmitting at 7, is that close enough to exactly 750? Yeah, that's probably exactly 750. So this is probably actually not an analog circuit of any sort. This is probably just a microcontroller and they're clocking this out. Actually, I know exactly where this is coming from. There's a this chip is basically a weird microcontroller made by what is it, NEC? It's called the LC87. But then they customized it for Wacom, so there's actually a little bit of custom hardware on this thing, specifically to generate the some of these waveforms. So this is actually a timer in that custom hardware unit in their weird firmware. So cool, now we're just locked onto the scanning pattern. Can we get that with the pen in frame too? We're gonna need... Oh, can we get this to hold still with hold off? Nope. Okay. So if we can get this to hold still, you can see that there's a long burst, which I think is used both to power up the circuitry and the pen and to help locate it. That's where we're looking at the analog levels of the resonance as measured by the tablet. And then right after that burst, we have what I think are ones and zeros. It looks like they're all the same right now. The pen is not actually touching the page. I'm hovering it right above because I don't want the pressure sensor changing. Okay, so here I'm clicking a button. And it's subtle, but let me see if I can put the cursor on it. Yeah, so if you look just to the right of that cursor, you might see that the waveform is either kind of ringing for longer or it's squished down a little bit earlier. It's really hard to see the response. We're mostly just seeing the carrier wave coming from the tablet right now. But I think if I get this receiver kind of on the other side of this, we might be able to get more of the response. So now I'm actually picking up not just the transmitted waveform, but I'm picking up the resonance in the pen's coil. So I'm gonna have to get it to hold still on the scope all over again, but you can see more of that like ringing waveform after each pulse. And I think that's what we're going to be changing with the button. One thing I've done before is to open up the tablet and get a signal I can use to stabilize the scope, like pull one of the address lines off the multiplexer chip. How can I high frequency reject this trigger? You know, it would actually be really useful to have a stable view on the scope as we take this apart. So maybe I should grab one of my disassembled tablets and we can grab a synchronization signal off of that. I mean, we can probably find a synchronization signal in there at some point, because it's going to need to figure out when that long pulse is and time everything else relative to that. Okay, let me grab a tablet that's already kind of disassembled. I think both of these tablets that have already been disassembled need an external clock source to even run. Yeah, we could use these, but it's a bit of a project to actually get one of these tablets running. So I might just open up one of these mostly assembled tablets and just tap off the signal we want. Which one? That one's empty. That one's firmware 1.13. I have a bunch of these that are all the same firmware version, so... So we're going to take apart this tablet, at least enough that we can get some reference signals off of it to make it a little easier to see what's going on the oscilloscope. Oh, that'd be a great idea. Grabbing a beer and relaxing. It is still morning here, but I should get some beer later. I'm out of beer. It would be nice to have something to drink in the evening. This has plastic snaps all over. This critter's dusty. I don't think I've had this open before. That firmware version sticker, I put those on just after plugging them in over USB. Didn't need those plastic snaps anyway. Okay. So, top panel. Delicious tablet circuit board. Shielding, which we can keep aside for now, but this is like electromagnetic shielding for the backside to avoid sensing on both sides of the circuit board. All right. So are the signals we want already on test points? These are the actual analog X and Y signals that go out to the antennae. These are the actual antenna grids. You know, not that super fine of a PCB, just like a pretty normal PCB with a bunch of traces on it. And so these are just a bunch of inductors that have been squished flat and then straightened out. So we went into this circuit before, but these are multiplexers, these are amplifiers. That's like a buffer. It's used for some digital stuff. I don't remember what that was exactly for. And then this is the microcontroller. A lot of these were actually ROM. So the way we've programmed these before was by using return-oriented programming in RAM. Oh, interesting. Dexter's Lab's wondering if the different Wacom Intuos pens could be retuned to make them compatible with other generations of the tablets. Oh, and Wacom made the tablets for the Quantel. Yeah, interesting. Yeah, that's a good question. I guess it would be interesting to see how reprogrammable the actual pens are. And it would be interesting also, like, my intuition is that the pens are probably using an ASIC. But I'm also curious if we could do something to make a pen that functions from just like an AVR running in super low power or something. Because I did an experiment a while ago where I successfully made an RFID card out of just an AVR microcontroller with nothing else attached. And it would be a bit of a stretch, you know, actually having working A to D conversion, but maybe the right chip would actually be able to make that work. Alexi's wondering if following the pen is about increasing the sampling frequency or just providing enough power. I'm pretty sure it's about keeping the sampling frequency high enough. It just wouldn't have enough time to scan the entire surface every time. So it takes a slower scanning pattern when it doesn't know where the pen is. Okay, so I don't remember exactly where these signals come out, but I think I just want to tap onto the GPIOs that select one of these inputs. So let's just trace those out really quickly under the microscope and figure out which test point they go to. So HC4051, these are analog multiplexers. I think each of these, no, maybe not. Well, so there are 4 coils coming off of each of these. 4051, how many channels is that? Eight channels. Okay. So pin 1 over there is a channel, pin 2 is a channel, pin 3 is the common that goes to this via, which I think is a bus that extends all the way down here. VCC up here on pin 16. Then we have 4 pins that are all coils, so that's Y2, Y1. I should show you the data sheet that I'm staring at here. Do I not have microscope and data sheet on my switcher? That's what I wanted, except without this. Yeah, so we've got a bunch of these. How many exactly? I think we have 4. So yeah, 4 analog multiplexers, each of which are 8 channel. And so I imagine half of these are for X and half of them are for Y. Anyway, I'm mostly interested in the selector bus, which is pins S0, S1, S2 over there at the bottom left. So they go under the chip and then out to those 3 vias, which I think we're going to find connected down to the same 3 vias on all of these chips. Well, there's going to be a different bus for X and for Y, but at least like the 2 pairs, I guess, are connected to each other. And we have test points. All right, so there's the 3 pins, picking up a 4th. No test points on that side. We might just have to stick a wire in there. Well, let's just stick an oscilloscope probe in there, actually, because I don't know which of those will be useful, but I think those are all actually pretty easy to get to with one of these little snaky things. That's the official term. Ground anywhere nearby? Not really. My ground is way over here. Just gonna scrape off some solder mask and clip onto the side of the circuit board. Let's see if that worked. Yeah. So these are just 3 binary bits. So it's not the best thing to trigger on, but we could probably use the pulse length trigger once we've got the pen in position. And these are just some of the bits that are selecting a channel on, I think this would be the y-axis because it's next to the y-axis coils, or next to the test point for the y-axis coils. I think that's the shared analog bus. Alright, I'm going to try to set this up the way I just had it. The pen and the coil and the oscope. We can get a little bit closer now. Oh, interesting. Yeah, Dexter, I don't know off the top of my head which resonant frequencies they use. I thought that both this one and the Intuos were 750 kilohertz, but let's, I have an Intuos. Let's check that one out too. So these are my electronics experimenting tablets, but this is my actual tablet that I use to get things done. And it's an Intuos Pro, what's the model number? PTH651. It's relatively recent. Put this aside temporarily. It's like a different song it's playing. It's searching a larger surface for sure. This is producing a much nicer sine wave. The other tablet, clearly this is all being kind of flavored by the pickup that I'm using, so the particular resonance of this coil. So maybe we're just getting closer to the resonance of this pickup, but something is causing it to be a nicer sine wave rather than the sort of triangle wave we were getting before. What is this approximately? This is looking a little lower, like 680 kilohertz, 666 kilohertz. 666 kilohertz it looks like from this tablet. Let's see if that keeps up when I put the resonant pen in there. Ooh. This might be a little easier to illustrate my point with, because the initial burst of sine wave. Did we just have a minor stream glitch? Anyway, that looks like it's about the same frequency in resonance, which is what you'd expect. And so right here, I'm mostly picking up just the initial carrier wave that's powering the pen rather than the pen's response. So like before, I'm going to try moving the pickup, so I'm mostly getting the signal from the pen instead. Not that far up. Ooh, pretty. If I hold it just right, I can get the scope to stay triggering. So I'm not using that external trigger right now because I'm not taking apart my Intuos tablet right now. I took it apart before and I scanned the boards, but I'm not going to take it apart again right now. Yeah, okay. So it looks like it's got a packet with a particular length which has been set up by the tablet. So the tablet's the one generating these pulses. The tablet is sending out that long pulse, and then the tablet is sending out a bunch of short pulses. But the pen, in response, uses those short pulses as timing and then changes the resonant damping of its LC circuit by like attaching a MOSFET across it, basically. And so it looks like it's sending back mostly one bit, like that's a 1 or a 0, and then one of those bits is the other. But I can flip the bits by clicking the switches on the tablet or on the pen. I'm having trouble seeing the change from the bottom button. That's interesting. I don't see a change from clicking the bottom button. I see a bit go away if I click the top button. Pressing the eraser doesn't do anything because I assume that only works when the pen is physically swapped. If I press the tip, then you can see a binary number starts changing up there. So that's the digital pressure gauge of some sort. I don't know why I'm not seeing anything from that first button. I mean, it's not a very stable trace, but I don't see it changing. Interesting. Let's try the other end. So I would also expect something here to be different to indicate that it's the eraser and not the pen end. So it's possible that that 0 is in a different position and it's just subtle. And here you also get a pressure sensor changing in that first set of bits. There's a question in chat about whether that only makes a difference when it's touching, but that's not how these work. That's just not actually how the pen works. It can sense where the button presses, regardless of whether you're touching the page. One theory is that yeah, I don't know. Like, I'm wondering if maybe there was some compatibility thing where they wanted this to have a protocol that was similar to an existing product that had fewer buttons, maybe. And so maybe the change that I should be looking for is different for that button, but that would be really weird. Is it in a different packet? Is my button just broken? So it's possible that I'm in a mode where this button isn't configured because I don't have the tablet software installed on this computer. I could try installing the tablet drivers and see if that makes a difference. It's conceivable it might put the pen itself into a different mode when the tablet is put into a different functionality mode. I think this gives us drivers for all the tablets, which is helpful because I have a few different kinds here. I've also got a different Intuos. It's a smaller, newer Intuos that I got, or not newer, but it's newer than these CTE 450s, but it is not as nice as the Intuos here. But we might look at that too. I don't know if I even have any pens that are compatible with that one. Grab that one while this is installing. Yeah, this is another eBay find that I have not shown on video yet. Wacom, no battery. So yeah, this one has USB or I think optional Bluetooth. I don't know if the Bluetooth is installed in here. My Intuos has a similar system where there's an optional Bluetooth accessory. I don't think it's present here, but maybe I'm wrong. Maybe it's just behind this thing. Yeah, maybe this does do wireless. That would be nice, actually. But yeah, I don't even know if I have any pens that work with this. I just picked this up on eBay because it was a random cheap find. I've got to unblock their kernel extension. This is great, right? Like, I don't even have to unlock this page to allow a kernel extension to run. Thanks, OS X. I mean, it's a great trade-off for usability, but it does seem like a big security loophole. Okay, are the drivers? Whoa. So we know about battery levels and stuff. This has definitely switched the tablet into a different USB protocol now, but I'm curious if that means that it's in a different pen protocol. So the pen seems to be mapped to the screen now. Okay, and that button works now. That's mapped to the right mouse button. This is the same button that we were not seeing on the O-scope. And then the top button is mapped to the first mouse button, it looks like. Maybe that's middle. What is that? Because, I mean, as usual, just like putting it down on the paper is the first button. And that's that's right click. That's got to be middle click. All right. Let's see if that looks different on the O-scope. All right, so searching for the pen. Oh, this tablet also has touch support. Which doesn't seem to be showing up much on this trace because that's capacitive, so I don't know. I would expect it maybe to show up a little bit, but yeah, let me turn that off though. There's a on-off switch for touch somewhere. So the buttons over here are actually touch sensitive, and normally when you put your hand on top of this, it shows you an overlay indicating which button is mapped to what functionality. And that briefly showed up and then disappeared, so I don't actually know what's going on with it. I'm gonna not worry about it. So just like before, I'm going to try to get the signal through the pen. It's definitely getting the right click. I'm not seeing an obvious change in the packet. It might be a one-shot thing, like it might pulse just for a single packet rather than... I mean, I doubt that though, because it lets me hold down the right mouse button and release it. I mean, it could be pulses for up and pulses for down. You know, that would make some sense if... oh, now the overlay comes back. Can I turn off touch? That would make some sense if it's trying to conserve the power in its onboard capacitors. Like if it can harvest power at all times except for when it's actively damping the coil with its transistor, like with an RFID card would. Maybe there's some reason for the protocol to only send back single pulses. I would expect it not to, because that seems less reliable. I don't know if I can catch enough on the scope to see a single pulse, though. We might need a different setup to do that. But yeah, it's weird that this button holds down just fine. This button... So I don't know what's going on with the protocol there. We might want to look at other representations of this. Like, if we were digging deeper into this, I'd probably want to take this apart and look at what digital signal this is extracting from all the analog that's going on here. But yeah, I think for the moment I'm going to put this back, and let's go back to focusing on the CTE 450 here. Let's see what's in here. So I wanted the scope just synchronized to one of those address lines we found. Let's get that set up. should 3D print some better oscilloscope probe holders. Yeah. Now we're actually triggering stably enough that you can see that the scanning waveform is not that stable. It actually jumps around a bunch because it's just a main loop running on the microcontroller here. And if it's interrupted or, it seems like the actual process of like sending out a ping and then measuring the response, that actually happens in hardware on this MCU over here. With like a custom peripheral, but then the actual main loop is pretty pokey and unreliable and just kind of ticks along at whatever rate it feels like. So this pen, I'm just trying to take stock of my pens again. This one, I thought this wasn't working before, but now I'm actually getting some motion from it. But the buttons don't seem to work. I think this was my working pen. Yeah, this one works from much further away. I think those other pens, I think if we take these apart, probably both of these are going to have cracked inductor ferrites. These were probably both dropped and then sold on eBay as broken. And then I bought them like a chump because I wanted to buy broken things that were cheap. Whereas this one is sensitive from much further away, and the buttons work. At least the right-click button seems to work fine, which is the one that's easy to test right here. All right, so like before, I'm going to try to pick up the signal through the pen this time. Maybe a better trigger. That happens to work out all right, actually, with just whatever settings I had in there previously. So I'm triggering on this long rising pulse here, which happens to be roughly lined up with the beginning of each scan. Great, and that's the pressure sensor. So the bits are not coming through that clearly. But hopefully you can still see the waveform changing there. The long tail seems to indicate like a 0, and the shortened tail seems to be a 1. So there's one of the buttons. There's the other button. Those are both making a lot of sense. Cool. There's the pressure sensor. And just to confirm the resonant frequency, I think these are 750 kilohertz, but let's zoom in. The least reliable way to measure the frequency. Yeah, so I had the cursor set to 666 kilohertz, which is what the N2O2 uses. And I'm expecting this one to be more like 750. Yeah, it's right in there. 750. There's a lot of extra space in the packet too. So that's the whole thing. I'll have to make a nice graphic in post where I show where all the bit boundaries are. And there's that 1 0, which I'm assuming indicates what tool we have. So I think if I flip over the pen, that 0 is going to move. Oh, we got a different 0. Cool. So that indicates that we have the eraser tool selected. And then these buttons aren't going to do anything. Oh, they do. Oh, neat. So that tells me this is all one circuit. I wasn't even sure whether the eraser half and the pen half were part of the same circuit on this pen. But so it has two separate coils, one on each side, two separate pressure sensors, but we can still use these pens. I guess I just never really tried that on this tablet because it's kind of ergonomically like not really something I would usually do. Like usually just erase and then you flip it over. But all right, so that's neat. I think it's maybe time to open this up. Let's try these tablets or these pens. Oh, interesting, look at that. It's damped every time. So either the coil in this is busted or maybe the damping transistor is shorted, or maybe the coil is physically shorted. It could be water damage that corroded the coil into, or corroded something into shorting. But this one is definitely looking like it's just permanently shorted out. And on this side, oh, not quite as bad on this side actually. Oh yeah, the eraser on this tablet kind of works. So it does seem to be a problem with the coil on the other side. It jumps around a lot, but it kind of works. Similar story over here. The eraser kind of works, but jumps around a lot. And this one, it just looks like it's shorted. Comparing that again to a working pen, which looks like this. It tracks smoothly. All right. Let's take, oh, I should keep the working pen and broken pens really separate from each other here. So this is the good pen. Let's keep the good pen and the mouse over here. Let's take apart this one that's got kind of a grimy front cap on it anyway. Oh, what good timing, camera, thank you. Okay, keep the scope handy so that we can scope out what's going on inside this pen. So it seems to already have a split right here in the middle that wants to come apart. This thing has been soaking in somebody's beverage. Okay. Hopefully that wasn't too destructive. So that was the eraser end. Did I lose any internal pieces? It looks like the coil was mounted inside the pressure sensor, both of which are separate pieces here. This is in contrast to the Huion pen, where the pressure sensing was done by detuning the coil. In this case, the coil is on a separate little ferrite here. This looks like nice Litz wire, too. We'll take a look at that under the microscope, but I think this is fancy wire. And so that's just fit in there. And then this is the actual pressure sensor, which I'm assuming is a strain gauge or variable resistor of some sort. Looks like kind of a coaxial assembly too. We'll have to take a closer look at that. Wacom silicon. I'll have to see if that could just be a microcontroller, but I would kind of expect it to be an ASIC. Configuration jumpers. This doesn't seem to want to come out easily. Just looking at this end briefly before we move on. It's mostly a hollow pen cap. That, oh, interesting. I think this actually comes out this way. Yeah, that goes through the ferrite and then presses directly on the pressure sensor. So you aren't pressing on the ferrite every time you use the eraser. Like that. This pen could be surprisingly usable after opening it, which is nice. So then this partially wants to come out. Any bets on how many pieces the ferrite's in when I take this out? The board is mostly free to move in this tube. It's just kind of caught somewhere on the end. That's not coming off. The nib is kind of falling out of place. I think the buttons are caught on this rocker assembly. I have a nice way of removing these buttons. I don't know if I have a nice way of removing these buttons. That's all right. So aside from being kind of gross, this housing seems intact. That coil looks a little damaged. Oh yeah, that's cracked. So the nib comes out separately. This is a user replaceable part. And then that is cracked. This has got to be the most common way for these things to die. I wonder if it's possible to fix these by clamping them really well and getting just the right adhesive in there. But I expect you probably have to replace the ferrite. Anyway, let's take a closer look at this under the microscope. You know, I might want to desolder this broken ferrite first thing because it's going to break really easily. I mean, it's already broken, but if I wanted to try restoring it in any sort of way, I would want to keep these wires from coming unwound at all, which is what they're threatening to do. Yeah, this is Litz wire. So this is done for low losses at high frequency applications. You use lots of tiny wires bundled together, which is what these are. So unlike stranded wire, these are all insulated from each other. They're like little enamel wires in a bundle. Yeah, you can see the multiple separate fine wires right there under the microscope. So that's the broken part on this pen. Yeah. I might try gluing that back together. Not really sure what else to do. And then while we're taking a look at this end, I'm curious about these force sensors. Like there's a thin rod on the edge, which is attached to, looks like this kind of rubber mat, I guess. And then that center pin. Interesting marks on these. So I assume there's an outer piece of plastic, this yellowish piece, and an inner piece of plastic that were pressed together and then like click into place, and then there's like a washer of conductive foam or something in between there that you're squishing. That's what it kind of looks like. Let's try to get that off. fingers are huge. Yeah, there's a pad in the middle that we're squishing, I think, to change its conductivity. And then that's actually the plunger that pushes on the pad. And there's a little cup that the end of the pin nib fits into. Yeah, there we go. And so this is, I think, the actual conductive material. Oh, yeah. Wow, there's a texture on the back of that I wasn't expecting. And then, is that metal disc? And then a spacer. This is hard. This isn't piezo, is it? Oh, it rolls away. Oh my gosh, is this piezo? Oh my gosh, it is piezo. I was expecting it to be resistive. So I think it was sitting like this. And so, okay, so this is just a retaining clip. The pin nib goes inside there. Let me put that in there for illustration. So the nib goes inside there, which fits inside here. I think that's what there was to it. There we go. So this is sort of like a little hammer. So the nib fits in here and then pushes a little hammer out through the bottom, that white piece, which then pushes on. So it's cushioned by this. I assumed this was actually the sensor material, but it looks like this is more like a cushion. So the hammer presses here, deflects the center of that piezo while keeping the edge of it stiff, I think is what that's for. I think that is just like a stiffening ring for the edge. And then this is a little piezo biscuit with 2 concentric electrodes. Wow, and then this part, I assume this is just gonna have some like pogos. Yeah, not even pogos, because we've already got some pressure, right? Because it's a pressure sensor. I think I need to swing the microscope up a little bit to get this. All right, and that's what the piezo was sitting on. Marble, your guess about the pressure changing the frequency, that's exactly how the Huion tablets work, but the Wacom tablets keep the resonant frequency constant. This is really nice, actually. This pressure sensor is much nicer made than I was expecting. I think that explains why these pens feel so nice. Yeah, and to be clear, so piezo, there's a relationship between charge and deflection. So if they just have a high impedance amplifier connected to this, they could just measure deflection pretty accurately. I mean, it does mean that gradually it kind of zeros over time, but I think you want that behavior anyway. And a lot of mechanical pressure sensors do something similar. There are a lot of reasons why you can't deform a piezo and get infinite energy out of it. I mean, if you start trying to extract energy from that system, I mean, first of all, it'll actually be extracting energy from the mechanical system also, but then there's also losses in terms of like heat and mechanical losses in the piezo. It's just a transducer. It converts energy back and forth. It's pretty common. Using a microphone as a speaker. If you can't always do, but you can do. You can almost always use a speaker as a microphone, at least. Curious how well this works with just one of these installed. And plug the tablet back in. Oh, such a good waveform, right? So this is, let me get that on the mic, or on the camera. I should really be recording all of this stuff separately. Let me start up the microscope recorder really quick, or oscope recorder. I figured I would want to include some shots of this in the video, and as much as I like cutting stuff out of the live stream capture, it's nice to have a clean capture. So I'm assuming it has a bit in there that detects whether the power is coming from this coil or that coil, and then just sets or clears the bit accordingly. And that's how it gets the eraser versus pen. But the rest of it seems to work pretty much the same. You still have this pressure sensing, and the buttons seem to still work. Yeah, let's take a closer look at this circuit to see what there is to see there. There are probably some interesting test points, well, points that we could turn into test points. And we might take a guess about what's in this chip, although it seems like it might be custom silicon. I don't know. Maybe we can try playing with its configuration options. I kind of want to put the piezo back together so that I don't lose these pieces or break it further than necessary. Don't quite have the patience to get reassembling this on camera, sorry. I think that would just slow down what I'm intending to be a kind of a quick process. So it's piezo layer and then the kind of rubber stiffness adjuster layer, and then the plunger and the retaining clip. And that clicks on there nicely. So I think that's reassembled. If we wanted to just swap the eraser coil and the front coil for experimentation purposes, that might be kind of nice. Anyway, so that was the piezo. That's where the coil attached, L1. So these jumpers are for tuning the coil. You can see each one is just connected to one of these capacitors, I think. And so you can choose how many of the capacitors get connected in parallel across the coil. So those are not configuration settings, those are just to try to get the pen resonance dialed in just right at the factory. There would be a combination of these jumper settings and I think the way they would do it is they would wind the coil according to some specification, but then there'd be some variation that they would be expecting, and so they would set up a set of these capacitors such that you can dial in exactly the right frequency there. So now we've got some different jumpers. We have some different resistors. I don't know what those are right away. There's a bunch of them. There's a bunch of resistors, a few of these 3-pin packages. I would expect to see some dual Schottky diode packages, so maybe that's kind of what we've got here. They might also be transistors. If we can find the modulation that it's sending back across one of those, it's a good bet that it's just a transistor across the coils. There's a thicker trace. There's a couple of thicker traces, actually. That might be ground. I mean, that's just connected to one of the coil leads. And a couple of pins on this chip. And this pour. And is that the other diode for sucking power out of these coils? So then on this side, there's, this is the eraser side. So another tuning network over here. Piezo seems to go directly to the Wacom chip. Goes to one of these underneath vias. So I assume this chip is going to have the A to D converter, the the kind of packet assembly shift register, all the timing detection stuff, just all the discrete logic we saw on the mouse in the form of 74 series chips. So I'm going to try to set this up so that we can poke around on this board with the O-scope. This might be nicer with the coil mounted remotely. I mean, I can just sit this flat on this board. I don't think there's anything that'll short out. I mean, it's kind of confusing to the tablet because now the pen is kind of all over the place. Like the cursor is actually just flickering around on the screen right now. Of course, the cursor's been doing a bunch of things on this computer. Oh yeah, I meant to bring up this paper earlier, which is why it was in the browser. There was a new YOLO paper, and oh geez, the mouse. Yeah, and it's a thrilling paper, written by the wonderful PJ Reddy, who created the algorithm that we're using for Tuco Flyer. And yeah, at the end of the paper, he's actually going on about like what this all means. And I'll just read this bit. But maybe a better question is, what are we going to do with these detectors now that we have them? A lot of the people doing this research are at Google and Facebook. I guess at least we know the technology is in good hands and definitely won't be used to harvest your personal information and sell it to... Wait, you're saying that's exactly what it will be used for? Oh. Well, the other people heavily funding vision research are the military, and they've never done anything horrible, like killing lots of people with new technology. Oh, wait. I have lots of hope that most of the people using computer vision are just doing happy, good stuff, like counting the number of zebras in a national park or tracking their cat as it wanders around their house. But computer vision is already being put to questionable use, and as researchers, we have responsibility to at least consider the harm our work might be doing, and think of ways to mitigate it. We owe the world that much. In closing, do not at me. I think I saw this zebra project too. Oh, that was linking back to page 4. Oh yeah, we're gonna measure some zebras. Wow, the great zebra and giraffe count. Number of photos per animal. Do you not have pictures of zebras in this paper? I'm totally here for the zebra pictures. I mean, this is cool too. That's pretty great though that they're using computer vision for animal census. Alright, is this gonna confuse my computer too badly? I'm at least getting a nice waveform on the scope, which is all I really care about. So the yellow trace is coming from that coil on the yellow probe, and then I'm synchronizing it using that green probe in the background. So I have to keep it pretty still or I'll lose my... Oh yeah, so I guess the synchronization is dependent on which zone on the tablet I'm in, which is why moving it mattered. I wouldn't be surprised if they actually have a fairly nice, like really low leakage input stage for measuring these piezo pickups. Let's see what other signals we can find. What do we even want to ground to? Presumably that thick trace. Yeah, I think I can just scrape some solder mask off there and get a ground. I would move the camera, except it's set up just right for this next shot I want to get. Try to get a ground and then maybe tape this down or something so it doesn't move as much, and then just probe around. I want to look at all the pins on this ASIC and see what they're doing. I should just solder a ground wire to this. It'll double as a handle. I guess I can get this on camera. That pressure sensor is really nice. I'm pleasantly surprised that they use those little piezo pickups. And this was never a high-end tablet. This was always a really budget tablet model. I'm kind of guessing that this is ground. It's attached to thicker traces on the board, and it's also attached to some packages which look like they're part of a bridge rectifier. Whatever it is, it seems like it might make a decent reference to clip the scope onto. Otherwise, we just have... Sorry. Otherwise, we have no reference. Get a good signal with this on the stick vise. Huh. I can get a great signal, kind of. There's a lot of damping there. There we go. Nice. Okay, 50 volts per division is not going to do us any favors. I assume this is going to be more like a couple of volts, if anything. So let's do 1 volt per div. There's our per packet synchronization of some sort. I'm just going down the pins in order, so pin 1 seemed to be nothing. This is pin 2, which is this ramp that's synchronized with the scanning pattern. Pin 3. Pin 4 is a nicer waveform synchronized with the scanning pattern. That's pin 4 of the ASIC. That would be a great scope trigger all on its own. It's pin 5, similar signal. Pin 6. Seven. 8, and I think 9 and 10 are both ground. 8 seems to have some subtle positive and negative going pulses on it. Yeah, I think that's real. They're pretty subtle, but that might just be crosstalk with one of the neighboring square waves, though. All of the signals we've been looking at so far seem to be related to either power or timing recovery from the signal. All right, so that was, I think, 10 pins on that side, so let's pick up with 11 on the other side. Okay, that's big. Is that connected to the coils or something? So just putting my scope across that completely changes the circuit's operation. I think that's connected to the coils. Huh. I don't know what's up with that long scanning pattern now. That's just from touching the scope probe to pin 11. There's pin 12. That seems to just be another representation of the demodulated data, but it isn't like completely demodulated yet. It's part of that circuit somewhere. 13, now that's digital. So now this is something where this is probably being used as a clock source. So the length of these pulses changes depending on whether we're squelching the oscillations in that our LC tank or not. We can damp the oscillation or we can let it ring longer, and that changes the length. I don't know if that's important. My guess is that this is being used as a clock signal, so it's looking for the distinct individual pulses. And this is pin 13. So pin 14. That's another more analog signal, similar to what we've seen so far. 15, this is just looking at the longer pulse, I guess. Huh. Pin 16. It's got a little bit more consistent duty cycle. Pin 17. Pin 18. Another thing that's, yeah. 19. And 20 appears to be power, which is about 1.2 volts. Well, where's the signal that it actually sends back? I mean, it could be this. One of these. When this is low, let's see if any signals that look kind of like that end up on something around here that might be a transistor. So some of these 3-pin packages are probably diodes. that? Those are the bits that are coming back. Where does that even come from? That'd be a lot easier to trace with the microscope. Oh, there it is. Oh. Huh. It's near pin 1, but I was having trouble picking it up from pin 1 itself. Oh, there's just some oxidation on that pin, so I was having trouble getting this earlier. This is actually pin 1 is the output signal. Well, yeah, what else is fun to do with this? I feel like this is kind of the basic demo. It would be really interesting to see inside this ASIC, wouldn't it? So this may be my first decapping project. I'm not really set up for that around here, though. Maybe I can send it to someone as a collaboration. I don't know. Like, we could do some more work to reverse engineer just what's on this circuit. It does look like the power recovery, like I think these two parts and these two parts are diodes. I think that's a MOSFET. I don't know why there's so many resistors. Some of that could be related to settings that we're providing. We could try to repair this broken ferrite. I think a drop of super glue and some clamping in the vise might help, but I don't know. It'll probably need retuning at the very least. Well, I hope that was an interesting teardown. Let me know what you'd like to see me do with this, and this footage will make it into an upcoming video about something. This is maybe you can see why I didn't go into this earlier, because it's not quite as interesting just like from a teardown perspective as the circuitry that we can fully you know, break down to schematic that we found inside the mouse. The ASIC is a little disappointing, but the force sensors in here are really cool. Maybe there's something we could do with those. I'm also curious just if they're useful at all as actuators, like if you can cause the tip to vibrate in a way that you can feel, like make a Wacom pen that has force feedback over certain surfaces. Could be interesting. Well, thanks for stopping by. Let me know if you have any ideas or if there's anything else you want to see here. I'll try to incorporate suggestions as much as I can. And special thanks if you support the channel on Patreon, if you send episodes to your friends, anything you can do to get the word out about what we're doing here, or just pitch in a couple bucks to help me pay rent and buy cat food. It'll help me produce more videos and just spend my time producing more things that I can put out there for free, rather than writing code that I can't release. So yeah, thanks for stopping by. A special thanks to everyone who helps out, and I will see you all next time. And so I've been trying to keep the schedule, well, the schedule is new, so I haven't been advertising it that much yet, but I've been trying to start them around like 10 or 11 a.m. My time, which I think is around like 6 or 7 p.m. Central European time, and just a little later in the day in most of the US. So yeah, let me know what you think about the schedule. I've been trying to do that on Tuesdays and Thursdays, but also just other streams whenever I can fit them in. So I had one yesterday that was pretty long, which is partly why I don't want to spend all day-to-day streaming, but I'll try to keep it regular enough to be interesting. Happy hacking, folks. I'll see you next time.